Okay, so welcome everyone to the ICTS string seminar. So today we're very happy to have Eric Perlmutter, which will tell us about harnessing S-Duality in N=4 and supergravity as Sl2z average strings. So over to you, Eric.
Thank you very much for the introduction and the invitation to speak at this series. The usual disclaimer applies. It's a shame I couldn't be there in person. I'd love to visit. Actually, over the holidays, I received an Indian cookbook just this weekend, cooked out of it for the first time. It was better than Indian food in suburban Paris, but not as good as Indian food in India. So hopefully I can visit in person in the relatively near future. But for today, we'll do it by Zoom, and I'll be talking about this paper with Scott Collier, which was written in January with the same title as the talk. Now, the talk is about S-duality in N=4 super Yang-Mills and the role of the symmetry in holography and the relation between all of these topics. So to basically quote from the beginning of our paper, we had two goals. The first was to understand how to extract the full physical implications of S-duality for the observables of N=4 super Yang-Mills, and ultimately, hopefully, other superconformal field theories with S-duality symmetries. And second of all, to put this in the context of IPhT, where the original duality between N=4 and type 2b string theory in IDS5 times S5 holds. And we'll actually be able to say something new about that, it turns out. So let me give a brief sort of introduction, and then I'll give an outline for the rest of the talk, and we'll get into it. So just to introduce the theory, we'll be studying four-dimensional maximally supersymmetric conformal gauge theory. And the N=4 theory contains a complexified gauge coupling tau, which can be written in this way, in terms of the topological theta angle, and G Yang-Mills, which I'm just calling G. And generic observables in the theory depend on tau. Being exactly marginal, tau parameterizes a conformal manifold, in particular an N=4 preserving conformal manifold, which therefore is one complex dimensional. And so observables define a map from the upper half plane to the conformal manifold. Now I've highlighted the fundamental domain for Sl2z because N=4 super Yang-Mills enjoys S-duality. For a simply laced gauge group, which I'll be implicitly assuming today, this is up to global identifications, a self-duality under Sl2z transformations of tau. The global identifications are important if you want to study extended objects or other such subtleties, but today we'll be studying the Sl2z invariant sector of the theory. And it's a strong weak duality, therefore. The S transformation of Sl2z maps weak to strong coupling, for example. And the point of view of the project was that the existence of S-duality is, to begin with, is established. So I'd say it's beyond a reasonable doubt due to copious evidence collected over the past 40 years within field theory and in the context of holography and string theory. Many of these involve the structure of the instantons. Some of these checks involve the 1/n expansion of things like 4-point correlation functions, where the Sl2z invariance of the coefficient functions is derived by independent means and then confirmed. And in the context of holography and string theory, well, as we all know, type 2b strings in 10-dimensional flat space are believed to admit their own Sl2z symmetry acting on the complexified string coupling. And the IDS5 times S5 compactification preserves this symmetry, thus furnishing a map between the conjectural symmetries of these two theories in the IPhT sense. We'll be concerned with non-perturbative observables, which I'll call O of tau, which obey an Sl2z invariance equation of this form. So if gamma is an Sl2z element, a non-perturbatively well-defined observable O, such as a conformal dimension, an OP coefficient, or a 4-point function of superconformal primary operators, obeys this equation. As I indicated before, there are observables that don't, for example, loop operators, but we won't be talking about those today. The story can be generalized, and I think that's interesting, but I won't talk about that here. And so the question is, for these observables, what is their explicit modular structure? This is a hard problem. Let me mention 2 reasons why. The first is that S-duality is inherently non-perturbative. So to understand the explicit modular structure of some observable, you need to have control over its coupling dependence for couplings of order 1. That's hard. Second of all, in the TUF limit, where integrability rules, S-duality is obscured because it's a double scaling limit where G is taken to 0. The statement is not that it's not there. It is, and as we'll see later, one can infer various consequences of this even in the TUF limit, but it is obscured. Now, one might say the conformal bootstrap can do non-perturbative things. Why can't it answer this question? And surely it can do non-perturbative things. But for example, if one is looking at a numerical plot of some OPE data, one's hard pressed to write down the explicit modular function which describes that data. So to summarize, n = 4 super Yang-Mills has a symmetry that we've not fully used. And what it would mean to use it from the, let's say, bootstrap point of view would be to systematically incorporate it from the outset of calculations, which then reduces whatever you're computing to its dynamical content with the symmetry consequences processed from the beginning. Not unlike using conformal blocks in computing correlators. So the idea of the talk is to apply a well-established spectral theory for Sl2z. That is to say, the harmonic analysis on the modular surface F. This is a robust tool that applies for finite n and for any such S-duality invariant observable. And one of the messages of the talk is that this gives a very different presentation of n = 4 super Yang-Mills from what we're used to. And for the calculations that we did, it actually turns out that once the framework is in place, there is a lot of output from just a little input. Relatively elementary calculations tell you interesting things. And so I'm hopeful that thinking more about this framework in the future will tell us more about this well-studied theory.
Can I ask a quick question?
Please, yes.
So you're really studying observables that are invariant as opposed to transforming as some weight, some modular function of some weight that's non-zero?
That's right.
Okay, so things like partition functions on compact manifolds and so on, those are not examples of observables. Because those typically, they do transform with some weight and there's meaning for it.
Yes, sometimes you can take derivatives of those objects and then you reduce them, you eliminate these ambiguities. For example, the force sphere free energy has these allomorphic and non-holomorphic ambiguities, but derivatives kill those, and then you get something Sl2z invariant. But there are some things where it's not so simple, and indeed, I'm not considering that kind of extended object today.
Okay, thanks.
Okay, I should say, other questions, please jump in anytime. Good. Now, at large n, this theory in the strongly coupled TUF limit is famously dual to type 2b supergravity, and ADS fashions S5, with a prescribed set of stringy corrections. And it turns out that the spectral decomposition we use reveals that there's an emergent ensemble average operating within this duality, and that can be phrased in the following way to be made explicit and more precise later. The large n limit of ensemble averaged n = 4 super Yang-Mills is equivalent to the strongly coupled limit of planar n = 4, that is to say, the supergravity theory. This holds at the level of Sl2z invariant observables that survive the supergravity limit, and this picture is meant to indicate an equivalence between, on the right, an average over the conformal manifold, then in the large n limit, and on the left, the strongly coupled TUF limit, where here I've put the theory at the cusp, and I'm asking you to imagine that you're taking lambda large as well. This observation has nice connections to some work done recently in lower dimensions about the appearance of wormholes in holography, and encourages us to study what we call the Sl2z Ensemble, which is just a fun name for the space of n = 4 theories parameterized by tau. And we'll see some interesting things there later. Okay. So the outline for the rest of the talk is as follows. First, I'll introduce the spectral decomposition I mentioned. I'll explain why it applies to n = 4 super Yang-Mills, and we'll extract some interesting analytic consequences of this for the observables of the theory. One nice benchmark of this, which I we'll talk about at least a little bit, is a certain integrated 4-point function that was studied in a beautiful paper by Doragoni, Green, and Wen, following some earlier work by Binder et al. And we'll find all our formulas confirmed when checked against this, and our formulas will sort of elucidate and explain in great detail why the formula for this integrated correlator looks the way it does. Those authors conjectured a formula for it, but we'll be able to explain its form. At large n, we'll make some comments about what this implies in the TÜV limit. Then we'll transition to the supergravity part. I'll explain the statement I made before. We'll study the Sl2z Ensemble a bit, and I'll make some remarks on IPhT at large, and then I'll conclude. As I said a few minutes ago, please interrupt with questions anytime.
I have a question.
Perfect. Yes.
So in the two equivalent field theory duals that you showed previously, is there any order in, like, how are you taking the limits? Like, is it n going to infinity first, followed by the Hooft limit, or like is the order relevant?
Yeah, absolutely. It's a good question. We'll hopefully this will be clear later. The short answer is to define the average, one needs to work at finite n for that to make sense. And then you take the large n limit of the average quantity. So that's one side. And then the other side is just the usual TÜV limit, then with the TÜV coupling taken large.
Okay.
It is important that one defines the average at finite n. It actually doesn't make sense to do this at large n. The two don't commute, averaging and large n.
I have a question.
Yes, please.
Is the understanding that in the strong coupling limit of planar n equals 4 SYM, the theory is going to become chaotic in some sense?
Yes.
Because you're taking the ensemble average of n equals 4 SYM in the large n limit, and ensemble averages usually imply quantum chaos. I mean,
Absolutely.
They are related to quantum chaos.
Yes, this paradigm does hold here. So the strongly coupled theory, as you alluded to, is known to be strongly chaotic, indeed maximally chaotic by certain measures, such as the bound on chaos. And the fact that the ensemble average lands you on this theory harmonizes well with what happens in lower dimensions. So
yeah, okay, fine, good.
Yes, so I'm saying yes, I think your intuition is good, and we'll talk more about that later. Okay. Very good. So a word on notation. Here's my notation for the fundamental domain, which will be this curly f. Tau will be x plus iy throughout the talk. So in field theory terms, y equals 4 pi over g squared. So large y is small g, a perturbative regime. I'll also write functions O as functions of tau, but they are non-holomorphic. So mathematicians usually do this. They'll just write O of tau, and without saying anything else, it's implied to be non-holomorphic. Sometimes we physicists write O of tau comma tau bar, but if you do that, mathematicians will say, what is that? So we'll be saving space and just by writing functions as functions of tau, but everything inside is non-holomorphic. Okay, so what are the elements of this Sl2z spectral theory that we need? It all flows from the following statement, which is that a square integrable Sl2z invariant function admits a unique decomposition into an Sl2z invariant eigenbasis of the Laplacian on the upper half plane. So the space of L2 functions on the fundamental domain has 3 subspaces. Okay. The first is a constant, so there's a piece that is independent of tau. I call this the modular average. We'll explain why in a second. The second piece is a continuous branch spanned by a continuum of non-holomorphic Eisenstein series. And a third, most mysterious subspace is an infinite but discrete branch of eigenfunctions known as mass cusp forms. if I have some function O of tau, which is square integrable and Sl2z invariant, it thus admits a decomposition that looks like this. Here's the constant term, independent of tau. There's an integral over the Eisenstein series with weight 1/2 plus it, where t is real, integrated over all t. And there are the Cusp forms labeled by n, where n runs from 1 to infinity. And the coefficients, of course, are the overlap functions of O with these basis functions. Now, before saying a bit more about these functions, here's a picture of the decomposition. Okay, so what have I plotted? There are 4 curves. I've taken some of these basis elements here and squared them and projected them onto their 0 Fourier mode, so integrated over x between -1/2 and 1/2. So the red line, let's talk about that first. Here I've just picked one member of this continuum, squared it, and projected onto the 0 mode, and I'm plotting it as a function of y, which remember was im tau. And this curve is smooth. There's some feature here. At small y, the numerics break down a little bit anyway, but this is a smooth curve. Okay. And this is in stark contrast to the other 3 curves, which are the 3 lowest eigenvalue Cusp forms squared, projected onto the 0 mode. Okay. So these 3 curves don't look like each other, and they don't look like the red curve, right? They're jumpy, they're sporadic, the locations and amplitudes of their extrema are sporadic, and they look rather chaotic, and indeed these functions do exhibit what's known as arithmetic chaos. Notice also, as a sign of that if you look closely, there are no triple intersections amongst these yellow, green, and blue curves, which is what you'd expect for chaotic functions defined as a function of one complex variable. Okay. So this picture is meant to indicate that there's a sort of chaotic piece of the decomposition, there's a smooth piece. Unfortunately, I won't have tons to say about the physical nature of chaos in n=4 super-Yang-Mills, but nonetheless, let's keep going. So now in a little bit more detail, we'll talk about this expansion. The constant is the modular average. Why is it called that? Well, it's just the overlap of O with the identity element, right? In other words, the integral of O over the fundamental domain. And all inner products here are taken with respect to the hyperbolic metric. So the average is defined like this. And we've just normalized by the volume of the fundamental domain so that the average of 1 is 1. And recall that the fundamental domain is non-compact, but has finite volume pi over 3. So that's the first term, that's easy. The second term is the continuous Eisenstein piece. So the Eisenstein series, you may well be familiar with these. They are eigenfunctions of the Laplacian on the upper half plane with eigenvalue S1 minus S, where S is the index. Here, S is 1/2 plus it. So these eigenvalues that appear in this problem are bounded below by 1/4. The Fourier decomposition is better written in terms of what one calls the completed Eisenstein series. So if we define this E star as the Eisenstein series times a completed Riemann zeta function, which is defined like so, then this thing is manifestly invariant under S goes to 1 minus S, essentially as a consequence of the functional equation obeyed by the Riemann zeta and a nice property of the Eisenstein series itself.
Sorry, I have a question.
Please.
I mean, what is the origin of this initial equation O of tau equals O average plus all these overlaps? How do you get this equation? From where do you get this equation?
The statement is that if O, so here this is just we're not talking about n=4 yet. If O of tau is Sl2z invariant and square integrable, then mathematicians have derived the fact that there is an eigenbasis, and I am writing this function in that eigenbasis.
And why are ES and phi n distinguished in some sense?
Well, yeah. So the phi n's are the set of square integrable eigenfunctions of the Laplacian. The Eisenstein series are not square integrable; they're almost square integrable. So notice they have power law behavior at large y. So actually, it goes like with an index 1/2, it diverges like root y. So it's almost square integrable, but I can't give a sort of deeper answer other than to say that one studies the solutions to this equation, given the hyperbolic metric, one gives names to the solutions, and then the hard work is showing that these things form a basis. That work was already done. So.
Okay.
So for example, maybe one useful remark is that one way to define the Eisenstein series for index s greater than 1, formally speaking, is as a Sl2z image sum of y to the s. Y to the s is sort of an obvious solution to the eigenvalue equation. And then to make it Sl2z invariant, you sum over images. And that actually defines the Eisenstein series. So I think that's a useful way of putting it. To get to this continuum where s equals a half plus it, one needs to do some analytic continuation, but that's the part that has been done. Okay, so what do we need to know about this Fourier decomposition? Well, note that the zero Fourier mode is a sum of two power law terms. It's manifestly invariant under s goes to 1 minus s. And the non-zero modes involve the Whittaker or Bessel function times some number theoretic Fourier coefficient. Okay. So I've written things here in terms of this bracketed overlap, not just the inner product, where I've just divided out by one of these so that we can write things in terms of the completed Eisenstein series. And as a consequence of doing that, this obeys a functional equation, which is nice. Okay.
Hello.
Yes,
so
hello.
So I have a question that from where this functional equation comes, this O es by lambda s. Is this defined or?
It follows from the fact that the completed Eisenstein series obeys its own functional equation. And that in turn is a consequence of Sl2z invariance. So the fact that E star s equals E star 1 minus s then implies that this does too, because of the way this integral is defined.
Oh, so it comes from the Sl2z invariance and the equation of O tau, right?
Yes, yes.
Okay, thank you.
Yes, so you can think of in spectral space, so to speak, this is the signal of Sl2z invariance. So these eigenfunctions are Sl2z invariant, but how is that symmetry reflected in the overlaps? Well, in this language, this overlap obeys a functional equation.
So you are saying that if O tau is Sl2z invariant, so the coefficient of OAS has to be Sl2z invariance, right? So from there it follows.
Yeah, I mean, these coefficients are numbers, I mean, functions of s, but not of tau anymore. But the reflection of their Sl2z invariance as overlap coefficients for a function of tau is that this coefficient obeys this functional equation. If it didn't, it would not describe the decomposition of an Sl2z invariant function. The other thing about the Eisenstein piece that one needs to know is that the overlap can be re-expressed actually as a Mellin integral of the zero mode alone of O. So this two-dimensional overlap can be written as a one-dimensional integral where only the zero mode of O appears. That will be important. So now the mass cusp forms. These two are eigenfunctions. They are labeled by a spectral parameter Tn. N is just labeling the members of this infinite series. And these are positive numbers, positive real numbers, where the lowest one, something like 7 point something, and they go on up to infinity. The fact that they exist is non-trivial. The fundamental domain is non-compact, but because it has finite volume, that is enough essentially to guarantee their existence, and their existence was first proven by way of showing that they obey a Weil's law of growth at large eigenvalue. There are similarities and differences with the Eisenstein series. Probably the differences are stronger. I've written the Fourier decomposition here of these things. Notice first there's no zero mode, so actually they decay at the cusp at large y. That's why they're called cusp forms. They have no zero mode, and as a consequence, they exhibit this exponential decay. And the Fourier coefficients themselves and the spectral parameters are not actually known explicitly in even a single case. By explicitly, I mean in some closed form in terms of some analytic formula, or even some closed form transcendental equation which determines them. What is known is, yeah, go ahead.
I'm just thinking ahead. Would you compute correlators or correlation functions of two operators and see whether they have the kind of structure that follows from chaos? I mean, the ramp and the Plato and things of that kind, because that sort of, I mean, is the same thing, right? Because you have this quantum chaotic regime and you're averaging over ensembles. So
yes, you are thinking ahead. Let me say just that there are different notions of chaos that appeared in that sentence, and they're not the same. So these functions exhibit what's known as arithmetic chaos, which I'll say something about in a second. That's different from the kind of quantum chaos appearing in, say, holographic contexts where you have Gaussian random matrices. These don't obey that such a strong form of chaos. And the connection between the chaos of these basis elements and the chaos that you see in strongly coupled quantum field theories is not clear. It would be very nice to understand that better, but they're not the same type of chaos and the connection is not totally clear.
Okay, thanks.
Sure. So indeed, so what is known about these? I mean, the fact that these spectral parameters and the Fourier coefficients are not known explicitly is a reflection of the fact these are chaotic objects. A great deal is known numerically, out to something like 1,000 digits of precision for the first many cusp forms. And if you look at large eigenvalue, then less is known numerically, although quite a bit is still known. But they are conjectured to exhibit arithmetic chaos, proven in some cases to exhibit certain forms of chaos, and believed to obey a whole slate of conjectures, some of which I've mentioned here, all of which fall under this umbrella of universal random behavior at large eigenvalue. So as I said, I won't have tons to say about how this manifests in the physics of the theory from the bootstrap point of view, say, but we will be able to say something. As one more sign of the chaos of these things, so here's a density plot of the Moss cusp form with spectral parameter given approximately by this. Black is maximum, red is minimum, perhaps the other way around. I once knew this, I forget. And we can ask, where is the global maximum and where's the global minimum? For the Eisenstein series, at least with index greater than 1, the max is at infinity, right, where they diverge. And the minimum is down here at the corner. For the cusp form that I've chosen here, the minimum and maximum are right in the middle of the fundamental domain. And if I were to change the spectral parameter a little bit, then these would move around. So these appear to be at random places from the point of view of a physicist, and indeed, they are literally in random places in a distributional sense. Okay, so now back to n equals 4 supereigenvectors. So what does this have to do with?
Sorry, just a question about this, these mass forms. So,
Yes.
So is there something known about the statistics of these eigenvalues?
Yes, thanks. So they are known to exhibit Poissonian statistics in their eigenvalue distribution, a large eigenvalue. And let's go back here for a second. So there's a lot of statistical things that are known and at least partially proven, and or if not that, then lots of experiments have been done substantiating them. So, for example, the Fourier coefficients themselves are believed to be bounded in magnitude above by 2 uniformly for all prime k for arbitrary cusp form n. This is the Ramanujan conjecture. And moreover, in between -2 and 2, they're believed to be equidistributed with respect to a semicircle distribution. So that's some of what is known, or at least partially known about these functions. But the general spirit is that at large eigenvalue, they can be accurately modeled by a random superposition of waves on the fundamental domain. But yes, they're rigorous.
It's not related to random matrices?
Correct. It's not that. Yeah, so it's not Gaussian, Gaussian unitary ensemble statistics. It's something weaker. And that's what the word arithmetic is meant to indicate. One way to think about why it is arithmetic chaos and not a stronger form of quantum chaos is that, well, Sl2z is an arithmetic group, which I think about in the sense that there's an infinite set of operators, so-called Hecke operators, which act on these functions, for which these functions are eigenfunctions, and the eigenvalues are the Fourier coefficients. And so there's this infinite set of commuting generators that add some symmetry to the problem and therefore reduces the amount of chaos, so to speak. I think that notion hasn't been made totally precise in the mathematical community, but that's how people think about it.
So is the understanding that if you chose the taus from a Gaussian random ensemble, a Gaussian unitary ensemble or Gaussian orthogonal ensemble, then it would have corresponded to normal chaos. Is that correct? Because taus are the couplings of the theory.
Yeah, no, right. So the things that we're talking about that exhibit chaos are the spectral parameters of this discrete of cusp forms and the Fourier coefficients. But let's forget about tau here because we're putting that in the
okay.
These are Sl2z invariant functions. What characterizes them? The eigenvalue and the Fourier coefficients. So let's study their statistics. And those are the things that exhibit arithmetic chaos.
But in general, if you have a certain Yang-Mills theory, the coupling is governed by the taus. And if you want ensemble average, if you want to ensemble average, then you have to ensemble average over the taus in some sense, right?
Yes.
Okay.
When you ensemble average, so here, if I want to well, we'll get to this in just a couple slides actually. Okay, so far this here is just the mathematical background. Now we should talk about what it has to do with n=4 Supergravity, and that's what I'm going to do. So the point is that well-defined CFT observables in any CFT are finite for all values of the couplings, modulo possible divergences at boundaries of moduli space. Now, in n=4 Super-Yang-Mills, what is the moduli space we're talking about? It's the one complex dimensional conformal manifold. The boundary is the cusp at infinity, but that's just the free theory, where observables converge to their free values. Therefore, the n=4 Super-Yang-Mills observables O that are Sl2z invariant are square integrable as well, and therefore they admit a spectral decomposition. So the cusp up at I infinity is just the free theory. So nothing divergent happens there. Right? And if you had some observable which somehow diverged in a free limit because of some recombination phenomenon or something, just renormalize it by subtracting the free constant value and then study that thing. Okay. And actually we'll see that the spectral decomposition naturally subtracts the free value. That is to say, when you develop the perturbative expansion, it starts at order g squared. Okay. So this is one of the main points of the talk, that you can apply this technology to n=4 observables. And the rest of the talk and the paper were extracting consequences of this. And two consequences come sort of for free.
Hello.
Yes, hello.
Can you just explain the second line a bit more? The cusp is just a free theory.
Yeah, sorry. So remember, tau equals x plus iy in my notation. Y is 4 pi over g squared. So small g is large y. That means large imaginary tau. And that's where you can get violations of square integrability up at the cusp. But that's just the free theory in the language of the Yang-Mills coupling.
Okay.
So I learned about these techniques in the process of a paper from last summer that I wrote with Scott and Alex Maloney and Liam Fitzpatrick and Nathan Benjamin. And there we were trying to apply this formalism to 2D CFT partition functions. That's much trickier and less natural, I would say. The reason is that 2D CFT partition functions, well, they're modular invariant functions of tau, where tau is the space-time tau. And large tau is you develop the Q expansion of the partition function, right? And at large tau, partition functions diverge exponentially. They go like e to the c times tau times a number. So you need to take care of that somehow. And so 2D CFT partition functions are not square integrable. But here it's a different type of tau, it's a different type of theory, and everything works much more cleanly. So what is something that this implies that doesn't take much work to see? It's a strong statement, and it's the statement that instantons are redundant in this theory. Let's develop the Fourier expansion of some observable O. We have the zero mode, and then we have the non-zero modes. The mode number is the instanton number. So if Q is e to the 2 pi I tau, you count the number of instantons, the number of anti-instantons, take the difference, and that defines the instanton number. So the claim is that the k greater than 1 modes are uniquely determined by the k equals 0 and k equals 1 modes. Where does this come from? Well, recall first of all that if you have the 0 mode, you can reconstruct the Eisenstein part of the overlap. Okay. So take the 0 mode, reconstruct the Eisenstein part of the decomposition. Imagine subtracting that out, and now take the k equals 1 mode, and the Fourier mode, the Fourier decomposition involves a Bessel function, but these Bessel functions with imaginary indices obey an orthogonality relation, which you can use to pick off the overlaps for all the Morse Cusp forms in principle, and then you're done. There's an important assumption here, which is that the cuspidal eigenspectrum is non-degenerate. This is unproven, but it's widely believed to hold for Sl2z. So as a picture of what's happening, like I said before, if the cuspal overlap happens to vanish, let's just say, you take the 0 mode, you reconstruct this overlap as the Mellin integral via the Rankin-Selberg transform, and you just plug back in, and then to get the non-zero modes, you simply plug in the non-zero modes for the Eisenstein series. Okay. So this is a strong statement. If you have the 0 and 1 instanton physics, then you have all the k instanton physics. The second thing that comes for free is the following. In a general CFT with a conformal manifold, we can define an ensemble average, which I'll use these angle brackets to define, as an integral of some observables O, which depend on some moduli x, over the conformal manifold with respect to some measure, which itself depends on x. A natural choice, though not the only one, is to take the Samological measure, where we use the Samological metric defined as the metric of the matrix of 2-point functions of exactly marginal operators. In n equals 4 Super-Yang-Mills, we can define this quantity. And thanks to maximal supersymmetry, the Samological metric is actually exactly equal to the Poincare metric. So what that means is that the ensemble average is equal to the modular average. And therefore, the ensemble average appears very cleanly in the spectral decomposition. We'll use this fact later. So to summarize the point of view so far, the essential content of n equals 4 Super-Yang-Mills observables lives in their spectral overlaps. And we now want to understand how the functional form of these overlaps is constrained by the physics of the theory. Let me pause and ask if there are further questions.
Yeah, I have one question. So you mentioned that the ensemble average just becomes the modular average. So is this a direct consequence of the spectral decomposition
No.
that's been done?
No, it's something simpler, which is that let's define an ensemble average in general like this, where I've chosen to use the Samological measure. Okay, that's the natural one, but it's up to me. Let's use that. And it's known that in n equals 4, the Samological metric is just the hyperbolic metric, the Poincare metric. So just this quantity is literally equal to the definition of the modular average integral of O, against dx dy over y squared. Now, on top of that, if I think of the spectral decomposition for O, well, the average appears as one of the terms because there is the constant subspace of the L2 eigenspace. So taking the average of O kills the coupling dependent pieces and leaves this behind. But the equivalence of the modular average with the ensemble average follows from much simpler facts that one doesn't need to use the decomposition to know about.
I have a question.
Sure.
So when you're talking about x mu, what exactly do you mean? Because x is just a single x. I mean, it's just
yeah. So here it's that's right. Here it's just one complexified coupling. So it's complex. So I mean, here this is the general definition of what you would call an ensemble average. In our context, this is just the x and y of tau. So tau is x plus iy, so it's to be d tau bar. Right? So. Okay. Good. So let me at this point actually ask how much time I have. Be sure not to go over.
Officially, you have like 20 minutes.
Okay.
But if you need more,
right.
we can also give you a little more.
Okay, thanks. Let's see. Good. So let me introduce this integrated correlator. I'll spend less time talking about this in view of time, but it's a really nice thing and provided some important checks for us. So take the dynamical part of the 20 prime 4-point function, which I'm calling this Tn here, and integrate it over cross ratios u and v against some measure which preserves supersymmetry. This exists, I'm not writing it, it's known. This defines what I'm calling Gn of tau. So it's just a function of tau. And it can also be defined in terms of derivatives of a free energy on the force sphere. This gives you a way to compute it because this quantity is computable by localization. This object was first introduced by these authors, as far as I'm aware. But Doragoni, Green, and Wen studied this and conjectured a really nice expression that's valid for all n and tau. The expression is a lattice integral representation. There's a two-dimensional lattice sum, a one-dimensional integral, an exponential factor here, and some kernel Bn of Xi. For example, for SU2, it's just this rational function, and for all n, here they're studying the SUN theory, I should say. For all n, it's just a different rational function where the degrees of the numerator and denominator increase linearly with n.
Sorry, I thought u and v were the real and imaginary parts of tau.
No, so sorry, that's x and y. But also here u and v are cross ratios in this top equation.
Okay.
Sorry, so think z and z bar, u and v. Yeah, sorry. So this thing here is a 4-point function, and you're just integrating it over space-time to get rid of the space-time dependence.
Okay.
What's interesting is that this can be done supersymmetrically, and nevertheless, you get a function of tau, but there's this nice conjectural expression for it. And the different values of n are related by a remarkable equation. The action of the Laplacian, on the one hand, can be rewritten in terms of a difference operator in n, giving you a linear combination of this thing for different values of n. There's another formal representation they wrote down, which is not well defined everywhere in the upper half plane, but nevertheless is useful, at least for us, which is as a constant plus an infinite series of Eisensteins with real integer index. And in this representation, the summand is given by, say, for SU2, this quartic polynomial, and for SUN, higher degree polynomials implied by this recursion. So this is a very striking formula. It raised lots of questions. Let me recast the form of this integrated correlator in the spectral language. So the claim is that the integrated correlator is given exactly by this expression. The coefficients here are the same coefficients on the previous slide. They're fixed by recursion from the n equals 1 and n equals 2 theories, with n equals 1 theory is taken to be the trivial theory. And there's a constant term here. And the claim is that this is the complete expression valid for all tau. You can see how we recover the formal sum on the previous slide in terms of Eisensteins by doing a contour deformation and picking up poles of. Now, there's an obvious thing about this formula, which is that the cusp forms are absent, strikingly. And moreover, the ensemble average is easily read off as this here. Okay, we'll come back to this periodically. Let me just say a little bit about the analytic structure of n equals 4 observables as implied by perturbation theory. Okay, so the obvious question is, how does weak coupling perturbation theory work in this framework, and how does this constrain the overlaps in turn? Note that this is insensitive to the cusp forms, which decay exponentially at large y, which is small g. So here's the zero mode written in generality, and large y is small g. We want to develop a large y expansion, so we're going to need to deform this contour to the left and pick up the appropriate series of poles. So this has to have poles in the right places, and the poles need to be of the right nature so as to generate only positive powers of g squared and no logs. So the most general form of the Eisenstein spectral overlap for observables in n equals 4 takes the following form. There's a sum of two pieces. The first is designed to give you the perturbative piece. Fp, where p stands for perturbative, encodes this part of the expansion. The values of Fp on the integers give you the weak coupling data of whatever you're studying, and the poles come only from here. So Fp is, with a small exception about s equals 1, which is a funny point, Fp is regular almost everywhere. Now, sometimes perturbation theory is augmented with non-perturbative pieces, either the minus y type instanton, anti-instanton contributions. So to this, we should add a function fnp, which is basically a regular function with no poles at these locations, because by definition, all the perturbative poles are here, but which allows the possibility of non-perturbative physics at large Y. These functions fp and fnp have to be reflection symmetric under s goes to 1 minus s. They have to be real so as to give us real CFT data. And as I mentioned, they're regular essentially everywhere. The asymptotics of this series, say whether it's Borel summable, convergent, divergent, etc., are encoded like so. So if we define the asymptotics in terms of some function Cn, or rather the expansion in terms of some function Cn, then Cn, right, just picking up the pole of this thing, is related to Fp in the following way, where this lambda is the completed Riemann zeta function, which appears because it appears here in the integrand.
Hello.
Hello.
Hello. What is this last condition? Tells this number 5 condition. If NPS is 0, then FP is entire.
Yeah. So,
what does it mean,
basically, what does it mean? So the claim is that each of these two functions can have a pole only at 1 or its reflection at 0. But if one of them, but together they must conspire such that the overlap evaluated at s equals 1 is regular. And so therefore, if one of the functions vanishes, then this thing has to be entire.
Oh, okay, in that way. Okay.
Mm-hmm.
Are you aware that this pi by sine pi by s into 1 minus s looks suspiciously similar to what you have for Gaussian ensembles for correlation functions?
I'm not sure the sense in which you mean that. Can you explain?
When you take the spectral density, the form of the spectral density in the various correlators, they usually take this form. If I remember correctly.
I think these quantities are sufficiently different that I don't see a relation, and but pi over sine pi s appears in lots of places, but I'm not saying there is no relation, but I don't immediately see why there would be one. But perhaps we can talk more after.
The relationship between, say, rho of the spectral correlator, for instance, rho of E and E prime. If you look at Dyson's papers, the rho of E and E prime has a factor which is suspiciously similar to this. I'm not exactly remembering what, but it looks very similar.
Yeah, I think I know what you mean, but I just don't, I mean, sine appears in lots of places.
E and E prime appears in the correlator.
These seem like sufficiently different quantities that I'm not sure if there's a relation, but perhaps there is, and maybe we can discuss more after. Yeah. Thanks. Okay, so let's revisit the integrated correlator in this language. So we've refined the structure of the overlap for general observables a bit. So let's recast what we wrote before. The cusp form overlap is 0. The non-perturbative part is also 0. And the perturbative part, of course, is non-zero. So this is quite simple. Two of these three functions vanish. And for SU2, the perturbative part is simply 2s minus 1 squared. And this is, in a quite literal sense, the simplest Sl2z invariant observable that you could write down in the SU2 n equals 4 theory. What do I mean by simplest? Well, something rather prosaic. The cusp form and non-perturbative overlaps are both 0. So the two functions that could vanish do vanish. The remaining piece, in conjunction with the constraints in the previous slide, must be a non-constant entire even function of s minus a half. The simplest such function is the degree 2 monomial. And this thing doesn't depend on other variables like cross ratios or temperatures or anything. So it's just a function of s. So it's a very literal way. This is the simplest thing that you could have. And I think this spectral language reveals the optimal simplicity of this observable even more than we knew before. Okay, so there's some more that could be said about the structure of perturbative physics and Borel resummations and so on. In view of time, I'm going to just quote a result, and then we'll shift to large N. So suppose there is no cusp form overlap for the moment. For simplicity, this can be generalized, but suppose that that's the case. Recall that the 0 mode then fixes the entire thing. Okay. Now you might ask, is the kth Fourier mode, the k instanton perturbative expansion, say, Borel summable if the 0 mode is Borel summable? Naively, this algorithm would suggest yes, because the latter is determined by the former, but the functional form of these modes makes that not an obvious statement. However, it is true, using theorems that constrain the form of this overlap, which recall is written as a Mellin integral, in terms of analyticity of the 0 mode itself in Y. And it leads to the following very simple relation between the convergence radii of the Borel transforms of the kth mode and the 0th mode. We introduced a certain modified Borel transform, which we call the Sl2z Borel transform. That's what B is. The details aren't critical right now. But if we define the radius of convergence of the Borel transform of the 0 mode as R, in the usual way, is the large order behavior of the series, and likewise for the kth mode, then the ratio of these radii is this very simple function, 1 plus k over r squared. And this is much stronger than what you usually get from resurgence analyses, which work at fixed k. Here we're seeing all k are related, and asymptotically, the Borel transforms are extremely simply related just by this quadratic relation. Let me skip this. This is a nice story, but I want to get to large N. So we introduced this main tool, the spectral decomposition. We explained why n equals 4 superangles observables admit such a decomposition, and then constrained them using the constraints of perturbation theory. And there were some other tools introduced along the way, or in this case, sort of not introduced. But the benchmark of the integrated correlator provided nice sanity checks and allowed us to see how nice this object really is. So let's talk about large N and then transition to supergravity. So we're in today's talk just going to talk about the Tuff limit. In terms of y, right, lambda is 4 pi n over y, and observables in the Tuff limit admit a genus expansion, at least perturbatively in 1 over n. It takes this form. You should think of this as an expansion of the 0 mode, because non-zero modes, and therefore the cusp forms, mind you, are exponentially suppressed in n. They go like e to the minus y, and y is like n over lambda with fixed lambda. Okay. So to develop the genus expansion, the algorithm is clear. We write the 0 mode in general. We exchange y for n and lambda, and then the key step is to understand how the overlap looks in a 1 over n expansion. We plug in and expand. Now, without explaining the details, and suppressing some coefficients and turning off the non-perturbative part of the overlap, although we'll see it return in just a moment, here is the form of what you get. So the 0 mode is a function of lambda in the genus expansion, looks like this. There's an average, which itself has some large n expansion. There's the sum over genera. There's this universal factor appearing in the overlap. There's the perturbative piece at genus G. And there are two terms here, which depend on n and lambda. These come from the two terms in the 0 mode of the Eisenstein series, the y to the s and the y to the 1 minus s. Now, the first term looks good. This looks like this will give us the usual lambda dependence of whatever it is that we're studying. The second term looks a bit peculiar at first. It's an Sl2z partner of the first term in the sense that we're starting with this Sl2z invariant eigenbasis and writing it in the Tuft expansion. and the zero mode of that eigenfunction has two terms. Because we're developing a large N expansion, we must deform this contour integral to the right and pick up the appropriate poles of this times this in S. But notice that consistency with the genus expansion requires that the expansion proceed in powers of 1/n squared. And that forces the poles in S to be at half integer values of S. Now, before fully processing that, it's already perhaps a bit strange, seemingly, that N is appearing here, right? The genus sum looks like all the N dependencies out front. But Sl2z is rearranging the 1/n expansion to associate certain subleading terms with lower genera. So what are some consequences of what we've just said? The first is that there's a simple large N diagnostic of non-perturbative, that is to say, instanton, anti-instanton effects. If you study an observable which at large lambda has an integer power of 1/λ, then there must be another contribution here. That is to say, the non-perturbative piece must be non-zero. Why is that? Well, the poles of this function determine the structure of the 1/λ expansion by contour deformation in the same way that they determine the 1/n expansion of this term. So if there's an integer power of 1/λ, then that would seemingly give an illegal power of 1/n, and that must be canceled by some other piece. That is to say, the non-perturbative piece of the overlap that we've suppressed here. So that's interesting. And in relation to that, as we mentioned before, Sl2z rearranges the 1/n expansion. So for example, if we develop the large lambda expansion, there's a constant term, which is a function of n, say coming from here and some small part of this. And then we have the sum over genera, and in each genus, there's an expansion in powers of 1/λ with some expansion coefficients. And then there's also these terms, right, which come suppressed by powers of 1/n with their own coefficients and with positive powers of lambda. You should think of these as renormalization terms. What do I mean by that? These are terms that regularize the 1/n expansion at large lambda. So for example, the first term here is an n to the 0 root lambda term. Right, n to the -2 times, say, an n squared here gives you an n to the 0. And this is dual to the 1 loop r to the 4th counter term in type 2b supergravity. The interesting thing about this is that it's associated with the genus 0 part of the sum. And the third consequence, and then we'll move on to the ensemble average story, is that if there are non-perturbative effects at large lambda, say e to the minus root lambda type effects, there are also non-perturbative effects in n. The argument, again, is rather simple. Non-perturbative effects in large lambda would come from divergent asymptotics of this. As you deform this contour to the right, if the integrand has factorial growth, you need to supplement, assuming non-Borel summability, you may need to supplement with non-perturbative terms, often canonically in n equals 4, as it turns out, in powers of this scale. But this function is also determining the asymptotics of this term after contour deformation. So for every such non-perturbative correction like this, there is a S-dual scale determined in terms of an S-dual TÜV coupling, which comes along for the ride. These have a very natural depiction in ADS. What are these? These are fundamental string worldsheet instantons, say, with points pinned to the boundary radius 5 times S5 if you're computing corrections to some correlation function. And the statement here is just that Sl2z means that there are also S-dual D-string worldsheet instantons in the bulk. So we see that Sl2z, even in the TÜV limit, has this consequence, and it gives you a certain class of non-perturbative effects in n for free, which is nice. Okay, so now transitioning to the claim made at the beginning and that side of the story.
So Eric, can I
Yes.
So in the TÜV limit, when you these additional these additional renormalization terms that you call, that means that what you called G in the initially is not the underlying G of the dual string theory. it's the combined power, which is the G, right? I mean the G. So this is, so the n to the 2 minus 2G that appears as a prefactor, that's sort of, I mean, yeah, I'm just trying to understand what is the physical interpretation of, so it's almost like there is a leading contribution and then there's a set of, then there are additional corrections. So the string theory at any, the dual string amplitude at any given genus G gets contributions from this little g and a whole set of other terms. That's roughly what you're saying in some ways, is it?
Yes, so that's right. This little g here is not what you would call the usual g in the string setting, as you said. It shuffles some of the terms around and takes, so some of the terms appearing there, this seems to be telling you, are better thought of as renormalization of loop effects coming from the lower genus vertices that one already has. So, so for example, the fact that this term is appearing as part of the g equals 0 part of the sum is to be thought of as the fact that when you do the one loop calculation, you need this, tree level counter term to cancel this effect, which in field theory variable scales like this. But we're supposed to think of that as, renormalization of the supergravity. We have our tree level action. We do a loop calculation. We need to add something, and so the fact that it's associated to genus 0 is telling you that that's what it's renormalizing, roughly speaking.
So it's that's what you mean by string renormalization.
Yeah. So right. So it's also the fact that it's a root lambda, right? So that's
so that's how did you I mean, the perturbative expansion was when you picked up the poles at s. I mean, so at negative integer s's, but now you got a kind of a strong coupling expansion in some way, is it? Or I mean, when you wrote it here in terms of lambda to the minus 3/2 minus m, that's you're picking up a different set of poles, which corresponds to a strong coupling expansion. Is that?
Sorry, yeah, I haven't been totally clear. So these two terms, these terms we should in general treat differently. This one we always have to deform the contour to the right because we're performing a large n expansion. So for any fixed lambda, then we will get these terms like this for any fixed lambda. Now at large lambda, we treat this by deforming the contour to the right. But say if you wanted to develop small lambda expansion, you would deform the contour to the left, pick up a different set of poles. And in doing that, there's a different constraint. This term is okay to be here at large lambda, and indeed it doesn't cancel with anything. But at weak coupling, you can't have a root lambda term.
Right.
And so that actually must cancel with something. But the polar structure to the right and to the left can be different. And indeed must be different for consistency. An important point here is that this FP of G at fixed G is not necessarily reflection symmetric.
Okay.
So that is important and not clear from what I've said, but that's true.
I see.
In particular, I mean, even just the fact that this has poles at these half integer values of S, that's a statement that's only allowed because we're doing the large n expansion first. Recall before that non-perturbatively, all of the poles were sitting here and FP was regular, but in the large n expansion, order by order, this can and indeed does have poles.
So you're saying that the first term in the brackets there, you can choose to expand it in strong coupling, weak coupling, and you choose the contour appropriately. The second term, you have no choice. But if you interpret it at strong coupling, it has a natural interpretation as sort of renormalizing the genus expansion. But at weak coupling, it doesn't have a it gives you non-analytic behavior, which you need to get canceled with some non-perturbative effects. Is that right? Or
almost, yeah. So you said everything exactly as I would have said, except for the very end, where what it cancels is not non-perturbative effects, but there's a correlation between different genera. So this term is n to the 0 root lambda.
Yes.
That needs to cancel against something when you deform this to the left, but it must be something at n to the 0. Okay, so that means it actually has to be a cancellation between the genus 1 piece of this deformed to the left and this genus 0 piece arising from deforming to the right. And in the paper, we write a relation between residues at different genera that ensures that this cancellation happen. And that's interesting, I think. We didn't explore it so deeply.
But there would be a root lambda. So there would be a seemingly a pole even from the first term, which would not be compatible with the usual perturbative expansion. But you need that to cancel a different order n expansion. Interesting.
Exactly. There must be a spurious pole at higher genus to cancel this lower genus. The spurious pole to the left that cancels this lower genus thing for which we have no choice. And I should say that all of this is confirmed and checked for this integrated correlator, which really was useful. You can check this statement very explicitly there.
Okay, great. Now that sounds very curious, very interesting reorganization of the whole Toft expansion. Yeah,
thanks. Yeah, thanks a lot for the clarifying discussion. Great.
Yeah, thanks.
Okay, so let me ask realistically how much more time I should take.
So how much time would you need?
Always a dangerous question. Let's say 10 plus 10.
Yeah,
10.
it's fine. You can take it. Anyway,
Okay,
I think people can just leave if they need to.
Yes, that's true. Yeah.
So feel free to continue.
Yes. Okay. So here again is this expression, and what I'm about to say is, I think, almost manifest already at this stage. There's this first term. This depends on n only. And everything here, if you were to expand it to large lambda, either dies with a power of lambda or a power of n. So all that survives at large n and large lambda to leading order in n is coming from here. Generalizing this to include FNP, giving the most general version of what I just said, and assuming for concreteness that the observable starts at genus 0, say of order n squared, the large lambda expansion is n squared times subleading terms in lambda with arbitrary coefficients, plus the leading large n piece of the average. So what this tells us immediately is that the large lambda limit of O lands you on the average. That is to say, the strongly coupled value of O is just large n limit of the average of O. And we can rephrase this holographically by identifying the large lambda limit with the supergravity limit as per usual. And then we have this equivalence. So let me again explain this picture. On the right, we imagine taking O at finite n, averaging over tau, and then we take the large n limit. That gives us this piece here. And on the left, we're imagining taking the planar theory and then taking large lambda. And this diagram is a slight abuse of that because, right, it's a double scaling limit where lambda is fixed, but I'm asking you to interpret the left in the large lambda sense as well. And so thinking of this cusp as the sort of extremal value in lambda space lets you draw a figure that looks nice. Okay. Let me actually skip this. There's a statement here that this extends to all genus by using this renormalization rearrangement fact that we discussed before, where if you take the genus G part of the average and take the large n limit, then that can be matched to the large lambda limit of O at genus G, a non-trivial statement which relies on this reorganization because divergent terms at large lambda at genus G are reabsorbed in the way discussed before. Yes.
So this correlator is supposed to be the dependent on the coordinates also, right? I mean, if it has to be a correlator, it has to be dependent on the coordinates also in some sense, or what is the interpretation here?
If O is a correlation function, then yes, these quantities depend on the cross ratios, but not on coupling.
Okay, cross ratios. But where do the cross ratios appear here?
Oh, they're implicit. So when I write O, I'm imagining it's any observable of the type discussed before, and that could include correlators, which depend on cross ratios. It could also be some thermal observable where it depends on temperature, but I'm suppressing all dependence on everything except for couplings.
And by cross ratios, you mean that you're talking about 4-point correlators?
That's what I thought you had in mind, but yes, or if it's a thermal 2-point function, then temperature, and of course, any separation, any other variable besides coupling is being suppressed.
Yeah, and when you talk about the 2-point function, when you talk about the 2-point correlator, since you have the entire non-perturbative series, can you kind of see whether it gives rise to confinement in some sense?
Do I have the entire non-perturbative series?
I don't know. Do you?
I didn't think so. No, I was wondering what you were referring to. So if you, this formalism doesn't give you, it tells you some nice things structurally, but if you're trying to compute something, a specific observable explicitly,
yeah,
it doesn't give you that for free. So for example, I don't have, I mean, at finite n, the story I just told, I don't have any great way yet, although maybe there are clever ways to use this in a bootstrap sense, to compute something like the unintegrated 20' 4-point function. One needs to find a way to compute that correlator. You can it must be recastable in this language, but the overlaps with the basis elements are not determined a priori. One needs to work somehow to compute those.
Okay.
So let me try to give some intuition as to what's going on here with this average equivalence at large n. Suppose you work at fixed tau in large n, sometimes called the very strongly coupled limit, instead of the TOEF limit. In this limit, what happens for some characteristic observable O is that the leading order large n limit is just supergravity, and the tau dependence appears in subleading terms in 1/n. So this term I'm taking to be order n squared, and there are corrections to this starting at root n and proceeding in negative half integer powers of n from there. And at each order, there's some function of tau appearing. Say if you're familiar with correlators or the effective action, you can Eisenstein 3/2 here at the leading order, and so on. So this suggests that to leading order in 1/n, where all of this stuff goes away, the average gives supergravity because there's no tau dependence. So the average of 1 would be 1. This doesn't actually prove the result that we derived. And the reason it doesn't is that the 1/n expansion and the averaging don't commute. These functions grow at large y, polynomially, and so they're not square integrable. In fact, they're not even, their averages diverge. Okay, so we can't average after expanding at large n. You might also wonder whether you can regularize somehow, but this doesn't give you the right answers either. So for here, I've just written a typical example. These are Eisenstein series. This is some generalization whose explicit form is not so important. But the corrections don't proceed in the powers of n that you actually get by the spectral decomposition. So the subleading term in general is of order n, not root n. And anyway, regularization a la Zagier, which is a common regularization of these functions in the string theory context, would set these two terms to 0 and this term to be non-zero. But in general, that does not actually match the subleading terms in the 1/n expansion of the average of O. So what our calculation does is that this intuition is confirmed in a rigorous way. So a couple comments. I want to emphasize that the traditional holographic correspondence still holds. We're not saying that one must average n equals 4 Supergravity to draw a duality with string theory and ADS 5 times S5. We are saying that there's an emergent average at strong coupling at large n, which is equivalent to the strongly coupled planar theory. And in connection with the question asked early on in the talk, the averaging generates a simple bulk dual. In other words, an extremal bulk dual, that is to say, the spectrum with the largest gap consistent with symmetries being imposed, i.e. the strongly coupled theory. It also suggests a possible plausible new strategy for deriving ADS5 times S5 supergravity from CFT. The strategy is, well, if the strongly coupled planar limit is equal to the large N average, then try to develop a theory of averages and take large N limits, instead of trying to understand the planar theory for all lambda and then taking large lambda limits. One reason you might be optimistic about this is that for an arranged CFTs in 2 dimensions, it was showed recently in some work that I should have cited here by Cohn et al., Afkami et al., and then also by Maloney and Witten, that the average spectral gap for an arranged theory is at large central charge scales like C. But that's not a result that one can confirm by scanning the space of large central charge theories explicitly. Instead, a calculation done there lands you directly on the average. And so one would hope that there's some theory of averages that one can develop in N=4 superangles, whose large N limits therefore give us supergravity answers. Okay, an obvious question is how this generalizes to other instances of ADS-CFT. In the paper, we articulated some scenarios without committing to any of them. We didn't study anything else except N=4 superangles. But imagining that we have some other conformal manifold M, possibly with some S-duality group S, and some direction G, which at strong coupling, say in some double scaling TÜV type limit, takes you out to some gravity regime where there may be other moduli. The general suggestion is that ensemble averages over M with some measure may localize onto supergravity, that is to say the strongly coupled theory. So we can demonstrate some of these scenarios by thinking about ADS3 times S3 times T4 as an example. In this case, it's a 20-dimensional moduli space. There is an S-duality group. And at large central charge, there is one coupling G, one exactly marginal coupling, where defining a TÜV type coupling lambda allows us to interpolate out to a classical supergravity at large C. And in this theory, there's a moduli space, which includes all of the other moduli orthogonal to the gravity direction, so to speak. So the question is there an average that could lead to a supergravity? And there are basically two natural suggestions. The first is if you average over all of M and then take this large C limit. And the second, more limited scenario is that perhaps you only need to average over this gravity direction G. These are essentially different. In the first case, we're averaging over everything. And in that sense, it's closest to what we did in N=4. But it's a little bit funny from the bulk point of view, because one way to say it is that the bulk is averaged. You're averaging over all of these moduli, even those that don't take you out to the gravity regime. But the answer might nevertheless be something simple, something like a consistent truncation. But perhaps the lesson from our work is actually, if you just average over the direction which is responsible for taking you out to the strongly coupled gravity region, then the other moduli should just come along for the ride. Okay, so which of these scenarios, if either, is actually correct, remains to be seen.
So what about the theories, the examples where we don't have a conformal manifold, like the 6D to 0 theory, for example?
Yes, I don't have anything to say about that. And of course, it's harder to imagine what one could mean by an ensemble average in that scenario. I mean, in the literal sense, there isn't one. So yeah, that if we think of those as really the typical examples of Holder correspondences, our work doesn't have anything to say about recasting how to think about those. Yeah.
I guess you could still average over N, right?
Yes. So, and now we're getting into issues raised by the Schlenker-Witten paper. You could average over N. That is not actually what Schlenker and Witten said to do, by the way. Sorry, I know I mentioned that paper, but yes, one could imagine doing some sort of averaging over N, or perhaps, take an average in some small window where you take large N and then allow some small window. Whatever that means, it's of a different nature than the more conservative kinds of averages I'm talking about here, although it might be interesting. Okay, so all of this motivated us to study the Sl2z Ensemble, that is to say, the space of n equals 4 theory is parameterized by tau, and the statistics of the data of the theory on this space. And so let me introduce a few equations, then I'll move my way toward the end. The simplest probe of statistical correlations is the variance. And we can define this as the average of O spec squared, where O spec is defined to be O minus its average. Now this is just the inner product of O spec with itself. And as such, we can insert a complete set of states, so to speak, and write down a nice expression in spectral space for the variance. Thinking of the variance as the second moment in tau space, we see this is basically equivalent to the second moment in spectral space. You take the overlaps, you square them, and then you integrate. So it's a very compact expression. And we can ask how this scales at large n by inserting, so let's drop this piece for now. It turns out to be suppressed in 1 over n compared to this piece for the first few orders. If we plug in the large n expansion of this and process, then we find that the variance relative to the squared average is down by 1 over n with a simple coefficient, where fp0 is the genus 0 part of the perturbative piece of the overlap. We can check this against the integrated correlator explicitly. So evaluating this for the integrated correlator, we get this integral. You can do it numerically. If you can do it analytically, let me know. We get this number. And so we're plotting that. So you have divided by the n cubed, right? So the average goes like n squared. So this thing goes like n cubed. And here's that dotted line on a plot of n versus this quantity. And now we can do a direct computation of the variance of Gn for finite values of n, starting from n equals 2 out to n equals 107. And you see that the scaling and the coefficient are both nicely confirmed. Let's not linger on that too much. So this begs the obvious question, what does this mean? What is the meaning of this variance in the context of ADS-CFT, especially given what's been going on in lower dimensions, in particular the JT random matrix story? The boundary theory is averaged in that story, and the bulk has space-time wormholes whose existence is meant to be explained by that average. Now, higher dimensional gravitational path integrals also appear to contain wormhole contributions. That's not a totally settled story, but there's plenty of evidence for some version of that statement, which has revived the factorization puzzle in higher dimensional ADS-CFT. I think it's important to take a moment to state the puzzle carefully. So as I see it, there are two components to the puzzle. There's a boundary and a bulk component. The boundary component is in a product of observables in two decoupled CFTs. Why is there a contribution that appears to correlate them? And when and how does this happen? For what observables? And what does the contribution, this correlation, look like? In the bulk, the puzzle is how do wormholes conspire with other bulk ingredients to restore factorization? That's a puzzle for the semi-classical theory. If you have a UV complete theory in the bulk, you want to know how this UV completeness trickles down to the semi-classical theory such that there's some sufficient set of ingredients that restore factorization despite the appearance of wormholes. So what does this have to do with our story? The point of view that I want to espouse here is the following. This large n equivalence suggests there's some gravitational manifestation of these Sl2z ensemble statistics. But how much does the semi-classical string theory know about these statistics? We're not trying to show that wormholes always dominate the semi-classical theory, and in general, they shouldn't. What we're trying to explain is whether and why the wormholes may appear as part of the bulk theory from the point of view of our formalism. And there's a useful analogy here with the half wormhole story of the Stanford group. Recall that for a single O, the spectral decomposition splits it into the average and then the coupling dependent part. We can think of this as the part that restores factorization, which was dubbed the half wormhole in that work. And the important point is that this constant piece is not arbitrary from the point of view of gravity. It's the supergravity piece. So if we now consider the product of O minus its average with itself, this splits in the spectral decomposition into the variance and the coupling dependent piece. And there's some analogy between the variance as a kind of wormhole and the coupling dependent piece as a kind of linked half wormhole in the parlance of this paper. So the variance appears naturally in the spectral decomposition sense, and is factorized observable in 2 copies of fixed n equals 4. And the appearance of that variance should be telling us something about gravity, precisely because of the fact that for a single O, the average is the gravity value. But what exactly it's telling us is confusing, and we don't understand it fully. Part of the reason is that the variance is down by 1 over n compared to the squared average, whereas typically wormhole effects are non-perturbative in G Newton, which is 1 over n squared. So where in the variance are the wormholes? What literally is the map between the variance or some part of the variance and space-time wormholes in ADS 5 times S5? And you could ask if this answer somehow depends on the choice of observable O, following some of the recent comments in this paper. Although I think there is harmony between these 2 papers, as it turns out. And finally, I would just point out that the question of wormhole amplitudes in ADS 5 times S5 is not totally settled. That's a separate matter.
Just
here's a summary of the
question,
talk. Yeah.
Yeah, I just wanted to know, so does the partition function is among the observables you can consider? Like, is it square-integrable?
Sorry, can you say again? I didn't quite hear.
Like, because in this wormhole story, people often consider the partition function as an observable. So is a partition function among the observables you can consider? Is it square-integrable?
So if it's Sl2z invariant, then yes. So you want to consider it on the appropriate space. So here, if we're imagining thermal partition function, like on S3 times S1, say, then I think it should be. And you could try to study something like the spectral form factor in this language. We haven't done that. I would, though, say that at large n, so this definitely deserves further study. There might be some subtleties with the existence of the large n limit that were brought up by this paper. But yes, I think that's something that one should try to think about in this context, although we did not do that.
Don't you expect it to match with some wormhole action in some sense?
Yeah, so
like if you do the 2 partition function combination.
Yes, if you could actually compute that on the boundary, then you would expect to see, I mean, for example, as conjectured in this black holes and random matrices paper, you'd expect to see some wormhole explaining the conjectured ramp and the spectral form factor for n equals 4 at strong coupling. Where that is in this formalism, I can't immediately tell you. That's part of the puzzle. And part of the reason is that the variance doesn't have manifestly wormhole type scaling with n. So what exactly is the relation when you have 2 copies of n equals 4? What is the relation between these Sl2z ensemble statistics and non-perturbative effects in supergravity is something that we'd like to understand better.
Okay.
The sort of converse question is, what is this 1 over n, the leading 1 over n term in the variance? What is that in the bulk? It's a little puzzling as well, because 1 over n is not a perturbative power. But that's a separate question.
Yeah, I was just wondering because, for example, Marvel centers, they have pretty explicit solutions, right? So,
yeah, I think their paper gives some of the best evidence that there are robust, stable solutions. They don't prove that, and so part of it, they don't actually work. So they do a lot of work in related spacetimes, by which I mean ADS 4 times S7 and so on. Then there's of course the issue that proving stability is much harder than proving instability. So I would say that it's not properly settled what is the space of wormhole amplitudes in ADS 5 times S5 string theory. And that's only talking about solutions. Then we can start talking about that wormhole amplitude in the sense of constrained instantons or non-solutions that we should be including in the path integral. And then that's a world that is interesting, but also not settled.
But shouldn't your proposal give a prediction for what, let's say, the variance of z of the thermal partition function should be?
I wouldn't quite go that far because so when you look at the squared observable, both of these terms, the variance and then the coupling dependent piece, when you expand at large n, they will interact with each other. And it's not totally clear to me which piece of the bulk answer comes from which piece of that boundary observable written in this language. I also think just the fact that there's a 1 over n, the fact that, so to say it another way, for a single observable O, the large n average is the supergravity value. We can then study the statistics of the Sl2z ensemble, but that's telling you about, in a sense, how strongly peaked the value of O is around its supergravity value. But once you start talking about variance around supergravity, you're getting away from strict supergravity. And it's not clear which ingredients of the bulk you're invoking when you do that calculation. Right? In supergravity, there is no coupling that takes you away from. I mean, there's a derivative expansion and so on, but the bulk is complicated, and which pieces of the bulk string theory map to which parts of the Sl2z moduli space in this ensemble sense is not clear from the formulas we've written down.
Okay, maybe I misunderstood something, but then shouldn't it be just like, let's say you have this partial function z of tau,
yeah,
and you're saying that if you average over tau, you get the supergravity answer, but
yes,
like shouldn't the wormhole contribution should just be like, let's say z of tau squared average over tau minus, the square of average of z of tau, just the variance of z.
Yes, but
this is something that should vanish if there's no average. So,
so, but there are different ways to average. So sometimes you can do an average over time. There's some, you can do a average over energy windows. I'm not sure.
Yeah, but here I was just doing the
relation is supposed to
Sl2z.
be.
I was just thinking of the Sl2z proposal you have.
Yeah,
I was just wondering if you have sort of this.
If in a fixed, so if I try to compute, say, the spectral form factor in a fixed doubling of n equals 4, this will not have that smooth dip ramp plateau behavior unless you average over time or average over theories in some way.
No, I agree. Yeah.
So
but
all those features are hiding somewhere in here.
Yeah. Okay. No, because I thought your proposal was that the average was to be over tau.
But the average was what? Sorry, can you say again?
Like the average should be over tau. Like
yes.
should be done over
yes.
tau.
Yes. For us, that's what the average means. Yes.
But then shouldn't give just a precise prediction for what this wormhole contribution should be, just because you just gave a definition of what it should be, I think.
So here I'm imagining O living in a single copy of n equals 4. So think of this in bulk terms as like a single boundary.
Oh yeah, but then I was thinking of taking 2 copies. Yeah.
Yes, but then we have this decomposition, and the identification with the bulk is not as direct because this piece has a 1 over n expansion. Okay. And so does this. And like, for example, whereas the argument given before that in the large lambda limit, all these terms are suppressed, it's not as straightforward to do that when you have 2 boundaries. That these 2 pieces interact more non-trivially when you develop that expansion.
I see. Okay.
That's the point.
I see.
Yeah.
Okay.
I have a naive question.
Yes.
The point is that since the ensemble average is finally going to get you the strongly coupled n equals 4 Yang-Mills theory, isn't that a conformal theory, and you expect that the correlator of say 2 scalars should be just 1 by x minus x prime to the sum power?
At 0 temperature, yes.
Yeah. So if you take the limit of this to the 0 temperature, what you have done. If you take the limit to 0 temperature by setting beta to infinity, do you recover that limit?
You must, as you say, by conformal symmetry.
Okay.
So let's conclude. That's a pictorial summary of the talk. There are various future directions to pursue. At this point, we've talked about some of them. And let me just leave this up and stop here. I'll take some more questions. Thanks.
Okay, thanks a lot, Eric, for the great talk. So, are there any more questions?
A kind of a vague question, but nice talk, Eric. Enjoyed it. So my question is about if you consider, I mean, the earlier part of your talk, this formalism that you outlined, which gives you a lot of mileage. If you consider something like M theory on a 2 torus, and you have the volume of the torus and the tau of the torus as parameters. You know that in the volume goes to 0 limit, this becomes the type 2b theory. And at large volume, it should become like 11-dimensional M theory. Now, if you considered something like the R to the 4th term in M theory in this context as a function of the tau and the v, can one get some mileage out of this? And can one basically say something about M theory amplitudes, which you, at least some general statements, like you said, which you couldn't perhaps do otherwise by considering M theory as the limit, the large volume limit of compactification on a torus, and knowing maybe the small volume limit is something like the usual type 2b answer. I'm just trying to, trying to see if there's some mileage there that could be.
Are you ultimately trying to understand what M theory on the finite volume torus looks like, or properly going to the
even maybe learn something about the infinite volume, but at finite volume might be useful if you're going to maybe use it as an interpolating parameter between type 2b and M theory. I mean, the R to the 4 amplitude in 11-dimensional M theory is just a number, and when you go down, it is you get some you get this modular function when you are at zero volume, but it might seem like that should be some nice completion for it's almost like you are the large volume, you're picking out a constant piece, which is like the constant part of your modular average. I mean, it's just a constant piece, whereas there's a non-trivial tau dependence at finite volume, and when you go all the way down to 0 volume, you get whatever the Eisenstein series.
I like that picture. I think so. One technical caveat in making that precise is that order by order in the alpha prime expansion in the bulk 2b theory, the coefficient functions appearing are not square integrable, and so strictly speaking, they don't therefore in your construction in that 0 volume limit, they don't actually admit a spectral decomposition, formally speaking, because that E3 halves is the function that appears there.
Right.
That diverges at the cusp polynomially. And so from the point of view of a regularized spectral decomposition, there's a way to deal with polynomial divergences at the cusp, which Zagier introduced.
Okay.
Which is basically to subtract them off in a modular invariant way by subtracting Eisenstein series. And so in this regularized decomposition, if you have a single Eisenstein series with some real index, then actually the regularized thing is just 0.
I see.
So in other words, in that case, you have y to the 3 halves growth at large y.
Mm.
How would you regularize that? You'd subtract off an e3 halves, but that's the function we started with.
I see.
So somehow what you said can't literally apply, but I haven't thought about this, and I like the idea.
I mean, the other ones grow even faster, right? The d to the 4, r to the 4,
Yes.
and so on. They're like e5 halves. I mean, and then it becomes even more. There are some other cusp forms. I mean, some, yeah, and some other
Generalized Eisensteins.
Generalized Eisenstein.
Yeah. So maybe perturbatively I mean, right? If you want to work non-perturbatively in alpha prime and tau in 10 dimensions, then you won't have this problem, presumably.
It's almost like the after the momentum space expansion you're saying, like in terms of d to the 4, that's like a increasingly divergent expansion. So it's almost like you're picking out some wrong set of poles when you're doing closing the contour in the S-plane. I see.
Yeah, and actually it's quite, so from the spectral point of view, that is how you see things working. So remember, for example, that so non-perturbatively in say n, the spectral overlap with the Eisenstein series of some O has this function which has no extra poles beyond those required by perturbation theory. But at large n, order by order, you do get extra poles at these half integer values of S. But it must be that if those were there at finite n, then this object would give you an inconsistent perturbative expansion where it generates powers of g, not g squared. So there is a flavor of that here.
Okay.
Yeah, so non-perturbatively in the momentum, somehow
so maybe
this function should be describable in this language.
So maybe r to the 4th is not the kind, or at least not expanded in this way. Maybe there's some other observable of M theory you can try to see if there's some way to. Yeah. Okay. Anyway, no, it's just a crazy thought. Thanks again.
Yeah, no. No, thanks for the crazy thought. The more the better.
I have another nice question. When you are doing finite temperature field theory, you are essentially working on a manifold R3 cross S1, right? But the theory is still conformal, right?
Sure. Well, I mean, it's sort of softly broken by the temperature, I would say. But
yeah, but in
basically
general,
still conformal.
In general, wouldn't that tell you that the correlator, the 2-point correlator of say two scalars, wouldn't deviate? I mean, it would deviate somewhat from the flat space limit, but I mean, don't you have an expression for that in general?
Well, not in such a strong sense as I think you're suggesting. That would admit some expansion in thermal conformal blocks, which depend on temperature and which in the 0 temperature limit land you back on the trivial 2-point function. But at finite temperature, there will be some these objects which encode the almost conformal symmetry, but there's more freedom in the function as a result of that breaking. But it can be nicely encoded in this block expansion. But the two do smoothly match onto each other.
But hasn't anyone worked out the explicit expression for
the explicit expression for thermal 2-point functions or for these blocks?
In finite temperature field theory?
In certain limits, but not in general. No.
For a conformal field theory, for instance.
Correct. Even in n=4, I think the answer is no. I mean, this does get. That gets complicated sort of more quickly than you might think. I mean, even a thermal 1-point function, if you're on the sphere across the circle, a thermal 1-point function is already quite a non-trivial thing. If you're on the plane across the circle, then there's a single constant. Those are new pieces of data. Now, if we talk about a thermal 2-point function, then there's an infinite set of OP coefficients, if you like. And so, no, I don't believe it's true that in n equals 4 at finite temperature, thermal 2-point functions have been written down analytically away from certain regimes of large dimension or low temperature expansion.
Okay.
And, does the spectral decomposition simplifies if you consider, let's say, supersymmetric observables, for example, because there is some interplay between S-duality and supersymmetry in type 2B?
Yeah, so the integrated correlator is exactly an example of that. That thing depends on tau, but is nevertheless supersymmetric. And as we saw, it exhibits this extreme simplicity. But it's an open question, I'd say, as to how supersymmetry plays with this decomposition. So for example, are there other supersymmetric observables for which the cusp form overlap does not vanish? The answer seems to be yes, because there is another integrated correlator. You take the same 20' 4-point function, you can integrate it against a different measure which observes supersymmetry. But that thing, for whatever reason, is much more complicated and seems to have cusp form overlap. So supersymmetry does not equal no cusp forms, for example. And generically, when cusp forms appear, that means that it will be hard, if not impossible, to write down an analytic expression for some finite unobservable in this language because you don't know the data characterizing the cusp forms themselves. So that is hard. So this formalism may not be so well suited for computing generic observables exactly, although that's obviously a hard problem from any point of view. There may be bootstrap methods which can be combined with this, which lead to something effective. That is something worth exploring. But yeah, I think it's fair to say that the cusp form, the absence of exact knowledge about the cusp forms is for some computations a weakness of this formalism. But for sufficiently nice observables, which can even depend on tau, like the integrated correlator, they may drop out. And for lots of questions, anything perturbative and anything in a Toth limit, the cusp forms drop out whether there's a non-zero overlap or not.
Is there any more questions? Oh yeah, maybe a last question, because we were discussing this in the journal club. Like, do you have any comments about this recent idea that pure 3D gravity can be thought of as Ensemble Leverage over the OP coefficient in some sense? Is this related to what you said?
I'm still trying to process the consequences of that yesterday's paper. But I think there's definitely a sense in which that seems to be true. Whether it's answering the sort of questions about how ensemble averaging relates to the space of CFTs or the space of near CFTs seems a bit open. I think there's a statistical nature to the setup, which would be nice to make stronger contact with the space of theories as we know it. And that's what some of the bigger questions are about ensemble averaging and ADS-CFT. I don't know if those are being answered here, but if nothing else, the connection between what is needed to reproduce all wormhole amplitudes in 3D gravity from a kind of minimal set of assumptions about the data characterizing the theory, it comes through really nicely in that paper. So that's my current understanding, but I'm communicating with some of the authors to understand exactly what they have in mind, and it's definitely an interesting story.
Okay. Yeah, thanks.
Sure.
So if there are no more questions, let me thank you again for the great talk.
Thanks a lot for the opportunity.
Thank you. So
it's fun.
Let me end the meeting now. So bye.
See you. Bye-bye.
Thanks. Bye.